Hi, I'm Antonio Sala, and in this video we will show the results of the simulation of the finite element model of this tubular heater and check what happens if we change the number of elements, if we change the beta coefficient that approximated the temperature distribution of each element, etc. In a previous set of videos, we already discussed how to model this as a PDE, the Laplace transform solution, the steady state temperature distribution, and the computation of a coefficient beta that gave me the mean temperature in steady state. So an energy balance led to this first order approximation, and we can cascade several of those first order approximations in a finite element model. By suitably manipulating the symbolic expression and converting them to numeric functions, we can call a numerical integrator simulation routine and obtain this kind of time response in which the dashed green line is the static instantaneous steady state model with no dynamics, and the purple line is the approximation. In here we have 50 elements, and we saw that ODE15 was kind of 5 times faster than ODE45, 0.12.64. If I multiply the number of elements by 3, then the execution time of ODE15 is 3 seconds, so it takes like 25 times longer than before, so 3 times more elements, 25 times more computing time, and in the case of ODE45, 3 times more elements takes 80 times longer. So it seems that if we are increasing the number of elements, the computational cost exacerbates, and ODE45, I will just comment this because it starts to be unmanageable. So now we have 150 elements. Let us look at the simulations. The steps in flow here and here, and the steps in heating power in here have a sensible transient. And indeed, if we zoom in, this is the response to a flow step. If the flow is constant, the partial differential equation is linear. So we had the Laplace transform solution, but in this case, changes in flow cannot be predicted by the Laplace transform model we developed in other videos. Nevertheless, well, it's kind of saying that if I decrease the flow, then the fluid has a longer time to cool as it travels along the pipe, so the outlet temperature diminishes after 100 seconds, which is the washout time in this pipe. My step in heating power has this kind of behavior that, okay, we proved in other videos that it was the truncation of a classic first order step response, and in theory we should be seeing that. We see sort of a ripple here, and indeed, even if it in here is barely noticeable, the ripple comes from the delay approximation, because the step in inlet temperature, its true response is a gain depending on heat losses after a time delay. So this is the approximation we have of the delay. This is kind of strange, okay, these high frequency oscillations. Okay, there is a video on the Padilla approximation on the delay in which this is explored in more depth. In here we see that this step response is kind of counterintuitive, but okay, this would be the exact response, and in here we see this kind of oscillation. Is this really bad? Well, okay, in here we have a sudden step increase of the inlet temperature, but if inlet temperature were smoother, this effect would not be so noticeable. See the referred delay approximation video for further insights. In here we have kind of a compromise between the exact value of beta that would perfectly match steady state gain, the stationary model, and another values of beta that would indicate a different temperature profile in each element. For instance, beta equal 1 would mean sort of piecewise constant temperature distribution. Then the issue is that a beta different from the exact exponential profile would lead me to a slight DC gain error, final value error, and also to a different, not so good in a theoretical point of view, delay approximation. Say if I put 0.6, you can check that this slope is kind of less steep than before, but now we eliminate the ripple. And if we zoom, then maybe we have, a slight DC gain error. But okay, this 0.6 value for beta seems reasonable to convince my customer, at least in the step response, that I am not doing silly things as the previous thing proposed, and it's reasonable. If I change it to 1, that would be the so-called all-pole approximation. Well, for symbolic stuff, let me change it to 0.99, otherwise it gives me an error, nothing conceptually important. And in here I traded off no oscillation at all, but a lower slope compared to the exact solution of the transport delay partial differential equation. So, in a particular application, we should trade off these high frequency artifacts versus the slope at the delay instant. But okay, that's only a problem for step responses in inlet temperature. The other plots are reasonably smooth, whatever the value of beta we have. In many control-related applications, if this is a subsystem of something much bigger, we don't want to devote so many computer resources to its simulation, so we may have a much lower number of elements. If I come back to the exact beta to match steady state, well, it's almost 0.5, which means a linear temperature profile. And in this case, of course, you see that we have these delay approximation artifacts are kind of less acceptable in step response. I have 1, 2, 3, 4, 5 oscillations in this transient, so I may be happier with a hand-tuned value of beta. 0.65 yields me a nicer solution, but okay, you see that the slope is not vertical as the theory should be. So number of elements, beta coefficient, it's kind of we decide. Balancing computational resources, step response artifacts, and overall accuracy. In theory, I should pursue a large number of elements to get a reasonable, good and steep response over here, and playing with beta, not so many delay approximation artifacts. As I said, the other step responses are good enough with no artifacts, steps in flow, steps in heating power. The green one is the instant steady state model that we would use if the duration of the transient is negligible compared to other transients in my system. And well, given that we have the whole simulation of all the states a long time, we can even simulate internal state. ODE15 did it. This is just plotting the ODE15 solution, some of the inner temperature elements, so that of course the elements closer to the inlet, when I put the heater on, well, they have less delay and less temperature, and this one is sort of close to the outlet, and these are the step response plots in the temperatures of the inner elements when I have a step in flow. Okay, this is close to the outlet, this is close to the inlet. So a vertical cut, which translates left to right, simulate, let's say, the temperature profile along the pipe as a function of time. As you see, the Pade-like approximation of the delay produces some artifacts, even if, of course, I chose beta so that in the last one, the last green stuff, the artifacts are only noticeable at the very end. Okay, so we'll finish here. In this video, that concludes the finite element simulation of a tubular heater. We explored how changing the number of elements and changing the interpolation coefficient beta influenced the time response. We conclude that only in the time response with respect to step inlet temperature inputs, these things were sort of important. The rest of simulations were reasonably good, whatever the value of beta was. We also saw that increasing the number of elements by a factor of 3 increased the computational time by a factor of 20 or even to 80 with some ODE45 code. So efficient large-scale simulation of complex systems needs a careful planification, and I'm not an expert on that, so you should consult other sources. In control engineering, at least for control design or modeling a subsystem, part of something much bigger, we usually tend to low-order approximations, say even the static no dynamics models or just the first, second, third order approximation of this PDE. In other ways, I get too complex models that take too long to simulate and are not that useful for control design purposes. So this is it. We end up here. Thanks for watching.